Welcome back. Back to IRT with Bayes for dichotomous data, not polytomous IRT. That's actually the next lecture. So, last time we discussed, I don't know if you remember this, I don't know that I'll call it an exciting lecture, but we discussed basically how to do IRT. We were going to take our example data and turn them into dichotomous items. We sort of discussed what IRT is, how you have a link function basically applied to the mean of your data, and that you're modeling that mean through a link function of some sort. Most commonly, that's the log odds or logit. I think we decided last time that everybody's team logit and not team probit, and then I had to go and say, but probit actually is a nice thing as well too. Am I familiar? Has anybody switched their allegiance? Do we have any undecided voters? I hear there's an election coming up. I don't know if you've heard about this. Believe it or not, like next Tuesday. Yeah. Anyway, shouldn't bring politics in here, but if the politics is between logit and probit, I think we're okay, right? I think in both ways you can just hold your nose and pick a link function. Sorry, probit for Kate. Thank you. There you go. All right. I should also note, and I didn't in these slides, but for those of you who've taken IRT, we often talk about, at least in the old days of IRT, I don't know that I'm part of that actually. I'm old, but I'm not as old as IRT, clearly. But when we started doing IRT, logistic or log odds was the first implemented. Actually, pardon me, probit was the first implemented. That was your two-parameter normal ogive. And then, two-parameter normal ogive. And then in the late 60s, we got into logits. And for a lot of the next 15, 20 years, textbooks would go out of their way to talk about how we could add a scaling constant to the logit, and we would basically get parameters that look like probit. I don't think anybody does that anymore as much. I don't know if you've seen that before, but basically the idea is if you multiply the result by some weird number, 1.701, 1.704, if you multiply in your logit for your IRT model, let's see if I can find where it is. Right here. You end up getting pretty close to the same results as well, so as logits. So logits, probits are often thought of synonymously. All right, we left off though talking about Stan. So any questions on anything IRT theory-wise before we get into IRT Stan-wise? I have to remember to drink iced tea this morning. Yeah, Ryan. Sure, no problem. So the question is about if you use the same prior, can you put two models on the same scale? You can. If you have the same priors between two models, that works. I think the question would be in the context of IRT, in the context of some models themselves. This is in the model identification step, right, where you sometimes estimate the latent variable variance and sometimes you fix it. Because the prior works a little bit differently on each of these parameters, the posterior distributions may not be identical. And I think that's the big distinction. They be very, very, very similar, but not identical. But you can always transform one to the other. Transformation is not a problem. It's just if you're starting to think of, let's say you want posterior distributions of certain parameters to be very somewhat. Pardon me, let me back up. If you once you set your priors and get posterior distributions for your parameters, if you then go and transform the parameters themselves, the posterior distributions are also, the posterior distributions are also transformed. And with that, when that happens, that transformation may lead to slight differences in the posterior. Does that help answer your question? No problem. Yeah. Yes. Yes, that's a great. Thank you for clarifying your question. Yes, yes, absolutely. If the scale is the same, if you've sort of used the same priors, used the same work, you can still do equating. Pretty much everything that you've done in any other context is the same. Oftentimes, we just use the EAP estimates of the scores. So you get, if you want to link one set of test scores to a different one, you use your EAP estimates. That actually is often the method used to go and provide scores in a non-Bayesian framework as well too. Yeah, absolutely, everything works the same. Does that help answer your question a little bit? You're welcome. And pardon me for my first answer. My first answer was sort of trying to define this property that posterior distributions may not be invariant under scale transformation. That's the big thing that I was trying to say. But from if you have the same posterior distribution standpoint, if you have the same sort of prior shape and so forth, any transformations of the same, like linking or other types of trying to put people onto the same metric still apply and still work in the same fashion. All right, other questions? Thank you for the question. All right, let's go back into Stan. I know I started this at the last with like 3 minutes left on the clock, so I'm gonna just restart these slides, and we'll start with model block again. A key difference here is that, as we saw last time, y now with a bracket just for item, and we mentioned this at the end, but I'll just point this out, that the syntax is slightly different than the CFA model. And actually, if I were to show you the CFA model syntax just to refresh the memory just a bit, grab this real quick here. So in the CFA model, you'll note y had a comma in an item when we listed it, and it followed a normal distribution. For the IRT model, it's slightly different. Y doesn't have a comma there. That's because we have to form y as an array. It's a slight change of how Stan works, but just be aware of it. Now what we're using is, we noted before in our lecture last time that IRT models use Bernoulli distributions with a logit link function, and it turns out Stan is nice to us in that it has a function called Bernoulli logit. Bernoulli logit takes the term inside the parentheses, which is on the real number line, and then converts it back to a probability using an inverse logit link, which is kind of what we saw here. Basically, if you could think of this whole thing right here is the Bernoulli log likelihood. What Stan is doing is taking your model portion right there and inserting it to where the probability in that log likelihood should show up. Before we called that pi. Okay? So Stan's doing all the intermediate steps for you, which is actually quite, to me, nice. You don't have to take mu and lambda times theta and back convert them to a probability using an inverse link function, the inverse logit, right? You can just leave them as is. It does it for you. So this looks very similar. Mu of item times lambda of item plus lambda of item times theta. So this syntax. As you'll note, we could have taken that for the model from the means in our CFA model right here. It's the same. It's just the Bernoulli logit function puts it into the link function. Okay? Then, Bernoulli logit itself, again, just uses that Bernoulli function. Everything else stays the same. Our prior distribution for theta will leave a standardized normal. We have lambda and mu here as well, which are multivariate normal distributions as well for each of those parameters. All of those could have been taken from CFA. All we've changed is the Bernoulli logit instead of normal, and just a slight change to how we call that using what's on the left-hand side in our notation. So the parameters block function is the same as well too. We have theta, mu, and lambda. You'll note there's no psi parameters. So here we had this psi parameter for the unique variance in confirmatory factor analysis, the unique standard deviation, if you will. Psi is not up here because we don't have it. The Bernoulli distribution doesn't have a spot for it, right? Once you know the mean, you know the variance. And finally, the data block. Now, this is the part where things are a little bit more nuanced. And the big difference is that when we define y right here, because we're using a Bernoulli-Logit distribution, right? Because, oh, that's not good. Because we've specified this Bernoulli-Logit, Stan will not let y be anything but an integer. Not only an integer that takes the values of 0 and 1, right? So how we define that in Stan is we define y as an array. For whatever reason, Stan reserves the word matrix as an array of floating point numbers, right? An array in computers is just like a matrix with more than 2 dimensions, effectively, sometimes. Although some of them can have weird, interesting features to it, like arrays of arrays and so forth. An array for us is like a generic box of data. We have to define the type of data, which means after you define the number of dimensions, right here we have 2 dimensions, one for items and one for people. We have to define the type of data, right? Remember, int stands for integer, which means all values of this array will be an integer, which is a whole discrete number, right? And further, I went and put the specification down that the lower bound of the integer has to be 0 and the upper bound has to be 1. Because now, if somehow we screwed up our data, y, and we put it into Stan, Stan would have an error if it was not a 0 or a 1. You might ask yourself, what if I have missing data? Anybody might be thinking, what's going on with missing data? The answer is don't. Just don't have missing data, and there's no problem. Okay? We all agree with that? I'm kidding. In a few weeks, I will show you code for missing data. The long story short with Stan is that Stan won't do anything if you have missing data. It will not do anything by default, right? In fact, it will just break. So we have to find a way to make Stan work with missing data. It's slightly more complicated, which is why I'm sort of layering what I'm teaching you until we get to that last part. Okay? Okay. So any questions on the array? Actually, there's one more thing before I ask that question. Let me say one more thing about array. The weird thing about array that drives me nuts, but it's just how it works, is that the order of the dimensions is flipped from what we normally think about, right? So that means the rows of this thing are items, and the columns of this thing are people, right? Remember in CFA land, when we defined y, it was a matrix, which means it's a floating point number. The rows of it were people, the columns of it were items. And so for our example, we have 177 observations in our data. A regular data frame that we used, don't ask me if it's tidy, because don't get me started on tidyverse stuff, but a regular data frame that we used before was 177 rows with 10 columns, right? As you would imagine, when we put that data frame into Stan this time, it's not going to work because we said that there are 10 items and 177 people. So it's expecting a data frame with 10 rows and 177 columns. And it turns out that's just a transpose, right? The matrix transpose just moves the row, interchanges the row position with the column position. It's almost literally like shifting it and turning it to its side. Going from landscape to, what's the other mode? Portrait mode, when you got a document, try to print stuff. So that's what the transpose does. The Stan data block is what we need for that. So this is a bit of a change. That means when we put data into Stan, we're going to have to remember to do that. Transpose our data frame. But that's the big difference. Okay, questions on any of this? Nice and quiet. That's what I like to hear. No questions. Crystal clear. Let's keep going then. I'm just kidding. Okay. So the data list itself. This is the part where I mentioned it has to be a bit different. And remember, when I build my data list, I literally go in order. Of course, I went to the wrong place. I go in order of what it expects in my data step, my data block in the Stan code, right? So I need observations, items, and y. Here you have observations, items, y, but y this time now has just the transpose function applied to the data frame. That t function in R just literally is a transpose. You can apply it to data frames, you can apply it to matrices, it makes little difference. Turns out what R will do is if these are floating point numbers in R, but they're all zeros and ones, they get converted to integer very quickly when we pass it to Stan. So it's fine to not make this a matrix of integers. Turns out integer is a data format in R, but it's rare that we use it. All right, questions on any of this? Negative. We'll keep moving then. All right, so we need to run this model in Stan. And this is one little catch of one problem that I didn't add to my slides here, and I should have, but running this is very similar to before. You'll note I do have my init function here, though. Do you remember the init function from last time? What was the purpose of init? Does anybody remember? Starting values, that's right. We need to set starting values because in Stan, our model won't know which direction to head when we initialize it. Right? Remember, there's these two modes in a psychometric model because we didn't observe theta. Right? Positive theta times positive lambda, or negative theta times negative lambda. What this does is sort of start Stan the direction that we normally would like it to be. You'll note I made changes to my CFA slides that actually implemented a second constraint that we talked about last time as well, which was we standardized the sum score of our observations, and we use that to initialize theta, our latent variable. I could and should have done that here in my IRT function, but you'll see it still works with just lambda being initialized. The other thing you'll want to note here is I'm initializing it a little bit differently than before. Before, I think I started lambda with a mean of 10 and a standard deviation of 2. But here in my R-norm function, I'm actually starting it with 5. Mean of 5, standard deviation of 1. The reason for that is because the inverse logit function, right? E to something over 1 plus e to something can quickly break, right? If I take e and I start, let's imagine I start my intercept at 2 and I have 10 for my lambda and I want to multiply that by a really large theta, maybe someone had a theta of 3, it starts to get a number that is very big, right? In fact, it starts to get really big. So sometimes, depending on certain software and how things start, having a really big value in an exponent is not a great idea in many ways. So I left this a little bit smaller. That's why the mean is 5. It's possible, although it's quite hard to do, but it is possible that if we get this number too big, we exceed numerical precision on the computer, right? Every computer system has its own largest number. In fact, if we go into R, we type the machine value. The dot machine is an object that sits in R, and it talks about the largest number the machine can have. That's our largest number right there. So if you wanted to convert that into, let's not convert that. But basically, that's the idea. That means if we somehow exceed that, if the exponent itself, the calculation for it exceeds it, what we end up with is a number that's an NaN, right? So if I take the largest number, or infinity, that's the other way. That's right. And then there's a, didn't quite do it either. Okay, so you know why that's happening though, right? I don't know, this is bad of me to say this, but basically the idea is I can't take an e of our largest number because that's exponentiating it even bigger. I'm just playing around with numbers here. But basically, I wanted to tell you that there is a maximum point that we get to with numbers. And rather than just play with R because it seems so familiar and comfortable with me this morning, I'll just tell you this is why. This is why I set the mean to be 5. We don't want it to blow up. All right. Once it blows up, it never stops blowing up, and that's a bad idea too. All right. Questions on that? I will reiterate one more time that in running Bayes for psychometrics in STAN, this is an incredibly important step, the initialization. Without it, you get these crazy results. So, but let's take a look at our results, shall we? Okay. First, let's check convergence. 1.001433 is the maximum R hat for all of our parameters. That's pretty good, right? Would you say this model has converged? Wonderful. Should we interpret some of the numbers? Shall we try? I don't know. Let's try it. Let's start with lambda. Lambda is like a factor loading. In fact, if it were factor analysis or item factor analysis, we'd call this a factor loading. But in IRT, it goes by the name discrimination. Right, the discrimination parameter. And so it indicates the change in logit for a 1 unit change in theta. So if theta goes up 1, right, if theta goes from theta to theta plus 1, we expect the logit to go up 1.9 points. Right? So 1.9 points in logit, is that a lot or a little? What is that? How do you tell? How can you tell? Okay, let's play around a little bit. Let's say a logit value is 0, right? And if I take the inverse logit of that, we get a probability of 0.5. But now if I take and put theta up 1, and it's 0 plus the 1.9 of that slope. Our logit's now 1.9, and our probability now jumps up to 0.86. Is that a lot? I think so. Probably a pretty big jump. All right, let's try it one more time. Let's take the logit and add another 1.9 to it. So let's imagine our original value of theta was 1.9, and our logit is now 3.8. Right? So our logit's 3.8. Now our probability is 0.97. Okay, so the first time we added 1.9, the logit went up by 1.9, went from 0 to 1.9, but the probability went up by almost 37 basis points, from 0.5 to 0.87. Now, the second time I add another 1.9 on the logit went up another 1.9, right? It's 3.8 for a logit. Now the probability's only gone up like a little over 10 basis points, by 0.1. Right, so that's the point we're trying to make. Logit sounds good, sounds important, but it's harder to say if it's good or not, what good is, because what good is on the scale is a little bit different for probabilities. But you can tell 1.91, I would say that's a fairly big value. Yes. Like in my practice of working in IRT models, we tend to think of discrimination parameters somewhere between 1 and 2, 1 and 2.5 usually. So 1.91 is right on line with that. But you'll also note that also is the smallest discrimination that we have. Take a look at this lambda right here. 13 or 21.6. Are you kidding? That's crazy. Have you ever seen a lambda or a discrimination of 21 before in an item? Can you imagine what an item characteristic curve might look like? A very steep slope, right? That would be very big. However, I'd be remiss if I said, yeah, that's 21.6, but look at the posterior standard deviation. It's quite wide. So we're not entirely sure where that number is. It's the credible interval is somewhere between 7, which is a little more reasonable, and 40.8, which is absolutely not reasonable for discrimination. All right. We'll stop there on discrimination. So I think we're pretty good. Do you have any thoughts on discrimination interpretation? Nah. I just led my question with it. No, you don't. You don't have thoughts. Actually, does anybody have thoughts? I promise. I do welcome your questions, and I try to treat every one of them with respect. Okay. But I don't see any questions. Let's go to mu. Now, this is where the slope-intercept form of IRT differs from our discrimination difficulty. And quite frankly, I like discrimination difficulty in the IoT world a little bit better, to be honest with you. But I'm teaching you slope-intercept because it's more generalizable right now. All right? So what do I mean by that? How do we interpret a mu parameter? Anybody want to take a guess? Anybody want me to give you a start? Good job. Theta equals 0, yep. It is the expected logit when theta equals 0. That's great. Another way of talking about it would also be the value of theta. In this case, yes, -1 times that is the value of theta at which a person would have a 50% chance of endorsing an item, right? So a person, this first item, which, do we dare even look what that first item was? Here, I'll go to the different screen. These are some crazy questions. Something about invading Iraq because of oil. You'd have to have a theta 2.5 standard deviations above the mean to even have a 50% chance of endorsing that item. It's pretty tough, right? And then you can think of it this way, the other way with mu. Some of these items are even lower, like item 8. All right, what do you think a person who's an average theta would be? Remember, our average for theta we set to be 0. So just imagine what the probability will be. So a person in an average theta would have, right, average theta on believing conspiracy theories has close to a 0% chance of saying yes to item 8. And item 8 was equally crazy. It was the NAFTA superhighway one between, I don't even know what that even does, but yeah, sounds good. Could use a superhighway sometimes, especially in this state. Have you driven in this state? A lot of left lane drivers out there. Never mind. I should leave it like that. All right. So, cool. How are we doing with all this? Sound good? All right. Vladimir. Yes. 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 Correct. Yes. Mm-hmm. Okay. Yes, that's right. Mm-hmm. Right, like a tenth of a unit. That's right. Mm-hmm. Well, yeah, I mean, if you go back to the original equation, let's see if I can get it right here, right? If theta is 1, your logit goes up by that much, by lambda. But if theta is a fractional value, it just goes up the same fraction of lambda, right? So if it's 1.1 for theta, it'd be increase of 1.1 for lambda, or if it's 0.1 theta, it'd be 1.1, something along those lines, right? Mm-hmm. Well, in that case, they're the same. It's not always the case that's the same. But when we fix the scale of theta by us specifying where did it go? Theta is normal with a mean of 0, standard deviation of 1. That really sets where we get to use how many units is a standard deviation, right? And actually, I think in statistics, we generally think of a standard deviation as a standardized unit, right? One standard deviation difference. It's sort of the basis for all our z-scores, all of our standardized mean differences, so things like that. So when we standardize theta, then increases in theta are usually relevant to standard deviations. If we had estimated this variance of theta, it's a lot harder to talk about it because now we have to sort of figure out what a standard unit increase in theta would happen to be. You're welcome. I will say for those of you who are in psychometrics and do what I would call the measurement part of psychometrics, right? Our goal is to give thetas, right? More often than not, standardizing the scale of theta is the most simple, most direct way of doing that, right? Like for me in grad school, I didn't take SEM till toward the end and didn't really understand it, but for most of grad school, that's all I ever saw was a standardized theta, right? In measurement. The times it changes is when theta, if we make it an outcome variable, remember the variance of that thing is now residual, right? And it has to change. Well, if you lock the variance in at 1 in this model and you predict theta, it can't change its variance or standard deviation. So what ends up happening is it changes all the other parameters altogether, right? And that's not a good situation to be in. So generally speaking, for this part of the class, we'll have this standardized normal. If you're going to use Bayesian versions of structural equation models, or let's say this, do you want to use theta to predict something? If this is let's say this is a like a test, like a college entrance test, like an SAT test, and you want to predict how well people will do in college, right? We could output theta and we can do a secondary analysis, but those tend to have methodological concerns if they're not handled the right way. The other way to do is build it simultaneously. Take theta and have it predict, college GPA, or better yet, have college GPA predict theta. That's really what I really should have done, and that variance will be reduced. All right, bad explanation off the top of my head, but anyway, back to the results. Any other questions about results here for any of this? Okay, let's move forward. So at this point, what we should do is go back and look at model fit. First thing in Bayes, convergence. Second thing in Bayes, model fit. I didn't talk to you about model fit because it also ups the difficulty level of this. We mentioned at the end of the last unit, model fit in Bayes comes in sort of two flavors. For what we call relative fit, there's the WAIC, or the leave one out, LOO, with Pareto smoothed importance sampling, LOOPSIS, which is the craziest acronym ever. Then there's also posterior predictive model checks for absolute data fit. In theory, the posterior predictive model check would work great here. We could compare and contrast our data to like generated data that we would come up with and see how well our model fits. And that's really important in a psychometric model, because if our model doesn't quite fit the data, these model parameter estimates, even their posterior distributions, may be off a little bit, biased, right? And if they're off, guess what happens to our estimates of our scores? They're likely to be off. So model fit, kind of important, but we're going to not talk about that right here. We're just going to pretend, and I will introduce model fit in a later class as well too. My idea for teaching Bayes is sort of scaffolding. Take models that you know and add and incrementally add to them. And that's actually a metaphor for how I build my Bayes code right now even, right? I had a colleague that wanted, random latent change point model, right? So continuous data, you have a change point function, you have to figure out where that change might be, and each person may have a different change point, right? Well, to get to that, guess what I started with? I started with an empty model and slowly built my way up, because if I started off with the random latent change point model and got an error, troubleshooting that error is nearly impossible. But starting with something that runs and adding to it is the step forward. So what I'm showing you here, and why I'm slowing down on this, is trying to get you to think about, if you're going to use Stan or Bayes for any of it, start simple, even if it's not the final model you want building, but that gives you a thing to test and add to that thing until it breaks, and that one thing that you added that broke it, you can go back and fix. Does that make sense? Cool. Bayes is not easy, is it? No. There's a lot of moving parts. So simplify. All right, but let's take a look at item parameters again. What I taught, we sort of interpreted item parameters before, but we could come up with a plot of the item parameters. And often item response theory, we use the item characteristic curve. I used that term in CFA before, but the same process holds. Remember, it was a plot of what our expected score on an item was. Like the expected score is on the y-axis, and on the x-axis is the latent variable value. Well, in IRT, our expected score comes from our inverse link function, right? So we vary theta, and we plug in values for mu and lambda, and we get our item characteristic curve. And so this is what we have. This red dashed line right here, this is for item 5. The red dashed line is our item characteristic curve if we only use the EAP estimated parameter values. Those EAP estimates had an intercept of -16 and a slope of 13. Oof, big one too. Okay, so that's our, if we were an IRT class, we'd just plot this red line right here. Right? And we could do a lot of discussion with it. We'd say, oh, what happens with our red line? Our red line is very close to 0 until you get a theta of about 1 standard deviation above the mean. And then all of a sudden it jumps up in probability very quickly, and it stables off right about when you get about 1.5 thetas. So within 1 standard deviation, you go from 0 probability to complete 1 probability of endorsing the item. So we'd say this is a highly discriminating item, is what we would say. This line is very steep, right? Now, what you don't see in IRT, although you could probably come up with a way to do this, are the black lines, right? Remember in Bayes, in my Stan model, I had estimated for each chain 5,000 iterations of warm-up and then 5,000 iterations of sampling. So I had 4 chains. I didn't thin the chain. Remember, thinning is removing a set of observations to sort of cut down on autocorrelation. I didn't thin them. I just ended up with 4 chains, each with 5,000 samples. So I had 20,000 values. And to be Bayesian, the posterior distribution talks about how plausible each of those values are. So it's actually and theoretically possible. So for every one of those 20,000 values, I created the black line, right? A little bit overkill, but those black lines kind of look like the spaghetti plots you might see, I don't know, in hurricane maps, the ensemble models, right? Or maybe longitudinal models. You see the spaghetti plots as well too. But this tells you, to me, the cool thing about Bayes is it's easy to sort of visualize the uncertainty, right? What do I mean by that, right? Well, take a look at where the mass of those black lines are. If we switch, in a couple slides, I'm going to switch from slope intercept to discrimination difficulty. But let's think real quick here. In a discrimination difficulty parameterization, the 50-50 point of probability represents the item difficulty, right? That's what we typically call it. And for our EAP estimate, that's somewhere around like 1.2, right? But if we want to talk about variation in it, look how wide that interval is, right? The point of where the 50-50 is somewhere ranges between, 0.75 all the way up to 1.5, right? So it could be a very wide range. We don't have a lot of information as to where that difficulty is. There's a lot of uncertainty in our parameters. That's what this is reflecting. I love the Bayes plots for uncertainty for it as well too. Any questions on this? How's your brain feel after an ICC that has all these spaghetti plots? Does it feel? Holding on to is it overkill? Is it too much? I think it's kind of cool, personally. Got a thumbs up. Thanks, James. Vladimir, question. That's a great question. Yes. Yeah, absolutely. If we, well, let's think about it, right? If we used a super informative prior, let's start with the slope, because the slope, let's keep it positive, right? The more a prior, let's imagine we changed our prior distribution. Let's see, what did I use? Where did it go? Didn't show it to you. Anyway, give me just a moment. My prior distribution for this used a let's CFA. Give me just a moment here. Oh, of course, I'm in the wrong folder. Hang on. Let me get the prior for you, and let's talk about what that looks like real quick. I used the variance of 1,000. So a standard deviation of 100. So very uninformative. Let's imagine if I use, instead of that, let's use prior standard deviation of 1. What that does with the prior mean, the mean vector was set to 0. That means the influence of the prior would be to force this slope, which right now is like positive 14, towards 0. So what we should see is the line gets flatter and flatter, right? But yes, I do think that the other thing that we would see in the informative prior is, if you look at, it's kind of hard to tell because the resolution of my black lines, they get to be a big black blob in the middle, right, of lines. But you can sort of see, look at the angle of where the steepness is for each, right? That indicates the variation in the slope, right? The steeper the lines means a higher slope. The flatter the lines means a lower slope. We'd also see that variation shrink as well, right? What the prior will do, the more informative the prior gets, you could start thinking about this as taking these lines and squeezing them together to look more uniform and more flat. And the limit of that, once we get the variance down to 0, will be that we will have a flat line, right? Where all the lines are parallel, and it ends up being right about at the marginal probability of a correct response of the item as well, too. So whatever proportion of people said yes to this item, that would be it. So Vladimir, to answer your question, yes, this variation will get shrunken with different prior choices as well. Kaylee. Great question. Why would you ever put super informative parameters on this? Wonderful question. To me, there are sort of two reasons. One is a pragmatic reason. The pragmatic reason is you won't get a model to estimate without it, right? There's not a lot of information in your data. So what a prior does is it takes your posterior distribution. Here, I have some slides on this right here. And makes a shape to it, right? So if this is the likelihood for theta, if the theta prior is more informative, this peak gets more pronounced, right? What that does is makes it easier for the model to converge to a posterior mode, because that shape is going to draw in those sampled values. Remember, the shape of the posterior is almost like a black hole, and things can wiggle around in it. Actually, I guess the black hole you probably can't wiggle around, but some type of gravitational pull, not black hole level, that allows some variation. The other time that you would, so again, pragmatic, informative priors are pragmatic. If you need a model to run, put them in, because results are better than others. Second time for me would be if you're doing an updating. So for instance, let's imagine this is a pilot sample. We have 177 people. we didn't really use informative priors so much. But for the next time, let's say I go out, that was my pilot study, and now I'm going to collect 1,000 people, and I want to go and update my information. It may be the case that I set my mean of my prior to 13 and my standard deviation to 9 or something along those lines, where I use my previous parameters' values because I want to update them to see where they would be. Now, there's one other caveat with the informative prior in psychometrics. Right? So an informative prior, we would all agree, something that's so informative that moves your posterior away from what looks like the data, will give you parameters that are somewhat misleading. And we can see that if we had done posterior predictive model checks, we would see that our model will not look like our data the more informative our priors are. But in psychometrics, there's a nice feature of the model that comes from this shape. Let me get back to where we were. This here, right? As lambda goes to 0, what happens to this item's information? It gets reduced to 0. In a 2-parameter IRT model, and actually I have slides at the end of this, we talk about the information each item contains about the latent trait, right? And that information in a 2-parameter model, the peak information is right at the item difficulty, and the amount of information is related to the value of lambda. So guess what happens if we were to put a prior information in, a prior distribution, a strong prior that forced all the lambdas to 0, right? What it would do is it would make it harder for us to understand where theta is. It would actually expand the posterior distribution for each person's theta. In many ways, to me, that's okay. That's not cheating with data. That's actually saying, let me be somewhat conservative, particularly in a measurement context. We always talk about, validity is quintessential for measurement, but reliability, if you have a valid test, but it's not reliable, you probably won't use it. An informative prior on our discrimination or factor loading parameters that sends them to 0 makes it so that we have less reliability in our result. To me, that's doing the least amount of harm in a psychometric approach. So I hope that answers your question, but gives a little bit more color to it. Great. I will tell you that in psychometric models, they're a little bit interesting. And what you're getting into for picking the choice of prior is literally the scale of the linear predictor. In logits, it's very different, right? A logit value, the reason is because the range of logits is so narrow, right? If I take a logit of 4.9, that probability is right about 0.992, right? So it's very big. And then, of course, negative 4.9 is the probability is close to 0, right? The complement of it, right? So what I'm saying is the range of logits exists between a linear predictor that sums to somewhere between -5 and 5, right? Now let's think about the normal distribution. The normal distribution center of mass is somewhere between, plus and minus 3 standard deviations around the mean. But in the normal distribution, the mean itself for an item, like in a CFA model, is going to be somewhat known. So like the scale of what those units are different. Logits versus points on the variable are different scales. So the impact of what makes a prior informative in CFA is very different for what makes a prior informative in IRT, simply because in CFA the lambda is on units of the actual observed variable, whereas lambda in IRT is in logits of the observed variable. So more information that probably is too much at this point in the class, but that's it. All right. This is, by the way, is our dinner conversation at my household. I'm trying to raise our son to be Bayesian, We all have these beliefs. Hey, you do what you want with your family. In our household, we'll choose our beliefs, and we're going to believe him to be Bayesian, all right? Sorry, just kidding. Never mind. I got to stop with it. All right, getting too close to political tension here. Let's make the political tension about Bayes versus frequentist. That makes it a lot more fun, doesn't it? Okay. That's right. Lisa would not push back against Hugh being a Bayesian. In fact, we're all Bayesians at heart, right? All right. These are the the posterior change for each of the item parameters here. Very interesting shapes to them, I think. You see a lot of downward amounts for the mu. That's because some of these items we have so few people endorsing with the positive, right? If you want to see why mu is so low, well, let's just keep moving. That is our posterior shape for mu as well, too. And here's our lambdas and our posterior distributions. Now, one thing you'll note, do these things, the posterior distributions, these posterior densities, look normal? Nope. Should they look normal? That's a good question. Anytime that someone uses the word should, it makes it feel like it's a moral thing. Come on, you distributions. If you were more like your father, you'd be normal. Never mind. But that being said, let's talk about it from an asymptotic standpoint, right? As n, the sample size, the number of observations per item, goes to infinity, what we should see is this converges, these posterior distributions converge to normal, right? That means, yes, we would expect somewhat normal-looking posteriors with larger sample sizes. But here they don't look normal. And that's okay. They don't have to be normal. They're just a posterior distribution. We're not making assumptions about it. We're going to use it. We're just not going to make assumptions about it. Also, the other thing I wanted to plot for you was this interesting relationship between certain parameters. We talked about this a little bit in CFA because to specify a prior, we could actually specify a joint prior where difficulty and discrimination have some non-zero correlation. So I just took, for the first item's posterior distribution of their intercept and the posterior distribution of that first item's loading or discrimination parameter, and I made a scatter plot of every draw, posterior draw. I'd say they look very positive, negatively correlated, right? Meaning as one of these parameters is sampled high, the other one gets sampled low and backwards, right? The other way around. I think that's somewhat interesting, but you can probably guess where that's coming from as well, because our logit, right? Inside the exponent, when you move mu up to compensate for it, lambda's got to come down a little bit to get about the same roughly weird posterior density. So this happens a little bit. You do see a relationship of the parameters being correlated. But that doesn't mean I would go in and put a correlation in my prior distribution. Like I wouldn't specify a prior for mu and lambda that used a correlated normal distribution. I would never do that. I don't know what that correlation should be. But it's kind of cool though, doesn't it? Have you ever talked about, in IRT class or other classes, have you ever talked about the relationship between discrimination and difficulty? Turns out there's even a group of people in the psychometric industry that believe it to be the case, and we can actually sort of see it here. Our two items that had the largest discrimination parameters also had the smallest difficulty parameters. So it's an interesting yoking of it. I don't know where I'm going with this apart from just noting that it exists, but I don't know other than that. All right, should we look at some thetas? I like theta. All right, here's your latent variable scores. By the way, they all converged. That's great. If I were to take the EAP estimates of every person's theta and plot them in a histogram, this is what it would look like. I have a very large number of people that have 0 for every item. And then I have much smaller people endorsing one or more items on the other side. That seems reasonable, right? One thing I will note, though, and I mentioned this earlier in the lecture, is that this big pile of people on the left here, the floor of the test, is estimable because we put a prior on theta. Right? If you look at any person's pattern of responses, if they all got zeros for every item, they all put 0 down, which many people did, the likelihood itself, the model data likelihood, is constantly increasing as theta goes to negative infinity. Meaning, if you're looking for a maximum of that model data part of it, you won't find it. But once you put a prior distributions on it, you do find the maximum, or you do find where it is. But the other thing that the prior does is not only gives you this value that's estimable, right? And you can even figure out which value that is. It's right about negative 4.24, right? All these people have the same thetas, roughly. There's some little minor variation in the second decimal place, and if we wanted that to go away, we'd run even longer chains. What the prior has done is establish a theta that represents the minimum score. That's what I'm going for. So it's not, so the Bayes sense is great in some ways. When I learned this in school, it was like, oh, this is a fix for ML estimates of theta. You put a prior on theta and you get estimates. That's great. But think of it this way, and philosophically, our choice of prior now is telling us that the minimum theta is going to be like negative 4.3 or 0.43, right? We didn't set that specifically to be that number. We said, oh, that's if we use this prior. So we're like one step away from setting the floor of the test is what I'm looking at. So don't believe that just because we put a prior in that we're not actively setting the floor of the test. Like I chose a prior for theta, a standard normal prior, but Vladimir picked a variance that's 1/2 that. Well, guess what? The floor is going to change also, right? So in many ways, putting a prior on theta is putting a limit on its range. It's an arbitrary choice. It's not. It's less subjective than saying I'm going to give everybody with zeros, one standard and -1. Like where some programs, after you look at testing manual, go look at the technical manual of some of the assessments that are operational. You'll learn about scoring methods and all sorts of stuff. And for some that use maximum likelihood, they literally pick what the maximum minimum will be. We're basically doing the same thing with the prior. We may not know the actual number, what the max is before we put the prior on, but it's going to put a max there, and that's what's going to happen. So, cool. Smooth distribution of EAP estimates. Here are two posterior distributions of theta, though, and I really wanted to compare and contrast this with CFA. Excuse me there it is. These were the first two persons in our sample and their posterior estimates of the latent variable in CFA. Their means may be different, but their standard deviations are about the same. Now let's take a look at that with theta. Big difference, right? Not only are the means for each of these observations different, the posterior standard deviations are much different too. And that's because in item response theory, or when you get away from normal distribution for your observed data, you now make it such that the posterior standard deviation for theta depends on where its mean is. Put another way, thetas have a conditional standard error of measurement. You saw that if you learned IRT previously, you will have seen this. We talk about it a lot. We actually leverage that conditional standard error of measurement concept when we build tests that are designed for certain precision points. Computerized adaptive tests, multi-stage tests, tests designed for flat forms with a certain expected information function. So our thetas have different posterior distributions. The person who has a smaller one just happened to answer items differently than the person with the wider one in a way that those items were highly informative. Well, we actually know that many of our items are highly informative based on our lambdas before, but we're going to talk a little bit more about that in this slide. Questions on this concept? No. Now, this is what I was really getting at. This is our EAP estimate of everybody's theta plotted against their posterior standard deviation. Right? So this is our posterior mean, posterior standard deviation, and you see a very familiar shape if you're into IRT modeling. Right? For lower thetas, they have a higher standard deviation. Right? As soon as you get to be a theta right around 1.5, you have the smallest standard deviation. And if you look at the scale of the y-axis, it ranges between 0.2 and 0.8. That's quite big. Those are very big values. By comparison, the same plot that I showed you in CFA, the y-axis ranged from 0.24 to 0.3, and really what this happened to be was just sampling error. I didn't run the chain infinitely to show it. So this is a very big difference, right? What we like to talk about in IRT is shown a little bit in this plot, in that the part where we have the smallest amount of posterior standard deviation, what we would call the conditional standard error of measurement for theta, is the part where our test is most precise, has the most information. So there's another plot that we tend to make called the test information function. I'm going to have that a little bit later, but it's sort of the flip of this, right? The flip being posterior standard deviation is sort of lack of information, right? So the higher values of posterior standard deviation means less certainty about theta, whereas information means, the bigger the information, the more certain we are about theta. So it's sort of a flip plot to this. Furthermore, we could compare our EAP estimates with the sum score. Now, this is very different from CFA. Remember, in CFA, it was very linear. This is CFA right over here that I'm showing you. But for dichotomous observed variables, our sum score and our theta change. And what I mean by that is, it's hard to see on this plot because we have a big pile of people at 0, right? 120 people down here at 0. But what you're starting to see is sort of a non-linearity to it, right? As theta increases, the expected sum score, or the sum score that you observe, goes up, but only, again, in sort of an ogive shape a little bit. All right. Questions on any of that? Great. Moving forward. Let's talk about reparameterizing a little bit. So I'm teaching this from the generalized latent variable framework, which is usually a slope-intercept form. But in IRT, if you just take it straight in educational measurement, you will see it listed this way. A times theta minus B is the term in the logit. Often it's expressed with the inverse logit right here. Right? The A parameter is our discrimination parameter. Theta is still our latent variable. But B is now called our difficulty parameter. So when you see a form of IRT that looks like I have on my screen here, we call that the discrimination difficulty parameterization. Right? The meanings of everything are roughly the same. I mean, difficulty means something different than intercept. But the idea behind the concept of it means something very similar regardless of parameterization. This is just a more familiar parameterization to people who work in IRT. And where I can show that these parameterizations are roughly equivalent is the following. If we take our discrimination difficulty parameterization and multiply A through, we're left with this number right here, right? Negative A times B plus A times theta. Now, if we wanted to do a little bit of algebra with this, right, just with this side of the equation, we could automatically say that lambda has to be equal to A. And if lambda has to be equal to A, then our intercept is actually negative A times B for an item. Or put a little bit differently, if we wanted to get to our item difficulty from our item, from our slope-intercept parameterization, it would be our intercept over A times negative 1. Now, one quick glitch with this parameterization, we can go back and forth between the two, but I will note if your A parameter tends to be estimated close to 0, you're going to have a hard time with this B. Because dividing by 0, we still call that undefined? One of you figured out what the definition of that is yet? It's not going to work though, right? I love math humor. I think if we could have more math humor in our life, it'd be better, wouldn't it? I feel like I'm a high school algebra coach yet. All right. We could actually go, though, in Stan and say, hey, wait a minute, you want a discrimination difficulty? Hey, we could code that. So we can go into generated quantities and build discrimination difficulty using the equations I did before. You want the A parameter and the B parameter? Just specify them here. No big deal. And when I did that, here are the results from our data, right? Those A parameters have to be the same because I specified them to be the same. But our B parameters now talk about where then B is an interesting parameter. We like it because with theta minus B right there, B is the value of theta to which a person will have a 50-50 chance of answering an item correctly. And why it's 50-50 is if theta and B are the same, the term in this parenthesis goes to 0. That means the numerator is e to the 1, which is actually just e, whatever that number is, over 1 plus, oh, sorry, e to the 0, pardon me, it goes to 0. E to the 0 means it's a value of 1, and then the denominator, this value is 1 also, so it's 1/2. Right, so we like where the b parameter happens to be there, and you can see most of our items are uniform in terms of where their difficulty happened to be. Somewhere between 1.27 and 1.78 we see. You could actually estimate this similarly in Stan if you'd rather not do generated quantities, and that's what I have here. Bernoulli logit of A times theta minus B instead. Same specification of priors. I also created generated quantities below, and you can get those numbers straight out. You'll note these numbers, though, are slightly different, right? When I estimated the discrimination difficulty model and I estimated the slope-intercept model separately, you'll note the b parameters are shifted. And this is the part I was telling you about, which is the posterior distributions are not invariant to transformations of parameters. But they're pretty close, right? Non-invariant means if you look at the scale of y and the scale of x, they're not quite on the same scale, but they have the same trend for what we do. And the same thing with discrimination parameters. You'll see that these are also different. And there's your plot as well. And there's our estimated theta estimates. The theta estimates turn out to be most similar as we go. And same with standard deviations. All right, so I got to stop here. I'm actually out of time. Sorry about that. Stop for now. I got a new formative assessment up. We got homework due the end of the week, and I got office hours with Vladimir and I tomorrow. You know where to find us. Thank you for your time. Have a great rest of your day. You got questions, stick around or come find us or somehow. Thank you.